Okay, so last week we talked about numerics for discrete optimal transport. Now I want to move on to the semi-discrete problem, which actually, the method that we're going to start talking about today is actually really one of the first numerical methods that was introduced for optimal transport and Monge-Ampere equations in the 80s, a method by Oliker and Prusner. In its original form, it's not necessarily the most efficient method out there. It's historically important, and the same kind of formulation, and we'll get to that, can also be solved now in much more efficient ways. So let's first try to write down the semi-discrete problem and just remember what we're trying to compute. So semi-discrete optimal transport. Okay, so this means one of my measures, mu, has a density. And one of my measures is going to consist of a bunch of Diracs. And let's say and they can have different weights attached to them. Okay, so when we're trying to solve this problem, we have some kind of smooth region, continuous region, that we're trying to map onto a bunch of discrete points. Okay, so what do we have? We have our usual mass balance condition. So just for this to be a problem that we're willing to look at, right? Total mass in here equals total mass in here, which the probability measures, then it's equal to 1. So we have that rho integrates to 1. And here, the lambdas tell us how much mass is at each point. So these should sum to 1. Okay, now we want to look at the optimal transport problem in particular, which means there's a feasibility conditions and optimality conditions that we need to look at for this map, right? So our feasibility condition is that we want the push forward of mu under the map T that we're looking for to equal nu. Okay, do you remember how we defined the push forward?
Mu of T inverse A.
Okay, mu of T inverse A, yeah, exactly. So here for my A, the things that are important, right, what's happening out here is not important, right? What's important is what's happening at these specific points. So I'm going to look at mu of T inverse of these locations. So if, say, this is yi that I'm interested in, then I go back and say, where did that come from? Well, it's not going to come from a point. It's going to come from a set. It might be this set. So this is going to be my T inverse of yi. Okay, and indeed, we want the mass in here to equal the mass at this point. So this condition is going to be that mu of T inverse of yi is equal to the mass here, which we called lambda I. Okay, and that should be true for I equal to 1 to n. Okay, and then we have from here the usual problem that this is our feasibility condition. We want to minimize, say, this quadratic cost. Okay, so what's the map going to look like? Well, it's not just going to be simply the case that, one point goes here, and one point goes here, and one point goes here, right? What we're going to have is regions getting mapped to each point. So somehow this support of our source measure is going to be decomposed into a bunch of different regions, and each region is going to go to a different Dirac mass. So somehow the problem really comes down to, can we find these sets. So we're going to take omega, our domain, and try to decompose it. Okay, it's going to be decomposed into n regions. I'm going to call them L1 to Ln. And each of these regions gets mapped to a Dirac. Okay, so with T of Li equal to Yi. Right, so this is really the game. We have our domain, and now we want to try to come up with what these regions should be. Okay, so we're working in Rn, say, or in a subset of Rn. We want to try to decompose this with respect to this set of discrete points, some fixed reference points for these y's. Do you know any techniques or strategies for taking a region and kind of decomposing it into a finite sets of regions, say, with respect to some key points? No, the answer seems to be no. What's that? Averaging? Like, how do you mean averaging?
The ones on the left are regions.
Okay, so obviously there's a lot of ways you could do it. So one way, say I have space, let's just say it's Rn for now, and we can stick boundaries on it later, and I have some points, and these are my fixed reference points. And I want to use these somehow to come up with a decomposition of space. You could do some kind of separating hyperplanes, yeah, and sort of the easiest way to do it might be, I don't know if this is the easiest, but it's maybe an obvious way to do it, is to just say, let's break this into which regions defined by which point they're closest to. So we have one region consisting of everything that's closest to this point, closer to this point than any of the others. One region that says we're closer to this point than any of the others. Do you know what these are called, this kind of decomposition? These are the Voronoi diagrams, exactly. Okay, so this is maybe an easiest thing to do, would be to break this down in terms of Voronoi diagrams. So this is going to be, let's see if I can draw this, something like that, that, that. Something like that. Okay, and these are the definition of them, right? The ith one is just defined by all the points that are closer to yi than to any of the other y's. So this is the set of all y in Rn, okay, such that y minus yi, I'll do square distance. Minimizing square distance is equivalent to minimizing distance, but squares are easier to work with usually. Okay, and this is for all values of j. Okay, so if you give me a set of points, these y's, I can certainly write down a Voronoi diagram, and there's fast algorithms for computing it. Of course, we have lots of freedom in how we could choose this row and how we could choose this mu. So there's no reason at all to expect that this Voronoi diagram is going to work for all possible choices of row. Of course, it's not, because there's a fixed amount of mass at this point. And if rho has a different amount of mass in this Voronoi cell, then we've violated mass balance. So this is not going to work just as is. We're going to have to tweak this idea a little bit if we're going to make it work. But this is kind of the foundational idea to these semi-discrete methods is let's adjust these Voronoi regions in a way that the amount of mass in each of these cells is equal to the amount of mass at the reference Dirac, and try to set them up in a careful way so that it actually gives us this optimal decomposition. So let's play with this a little bit. Let's say we zoom in here at some yi, and this was our cell vi. Okay, we know that we want mu of vi to be equal to lambda I, which it might not be. So let's say it's not. Suppose we have too little mass in this cell. So let's suppose, actually this is the case when we write down our Voronoi diagrams, or it could be the other way. So right now, vi contains too little mass. Well, what might we want to do? We might want to try to increase the size of this region. So we might say maybe we can push these boundaries out a little bit, right? Try to make it bigger. Push it out until we have the right amount of mass. So let's, in other words, try to shift the boundary lines of this cell to increase the amount of mass. Right? In other words, somehow we're assigning more weight to this cell or to this mass, right? Instead of saying, let's just pick the points that are closer to this than to everywhere else, we say, well, we want a little bit more than that, right? You know, we want to be closer to this modulo some weight that decides really how important this is. So what are we really asking? Instead of asking y minus yi squared to be small, okay, relative to the other distances, relative to the distance to the other Dirac, we're going to ask something else to be small, something that's easier to make small, something that's going to be small in a larger region. So let's ask y minus yi squared minus some adjustment to be small. Okay, for some weight function. Okay, so what does that mean? It means we go out here and say we're in this region. Y minus y squared is bigger than y minus yj squared out here. But that's not what we're comparing. We're going to take a little bit off of it, make it a little bit smaller. Take this, make it a little bit smaller, and then compare it to y minus yj squared. Right? That's going to give us this bigger region. Is that okay? And you could do the other way around, right? You could look at this and say, actually, there's too much mass in here. We need to move these lines in. Then what I really need to be doing is using a negative weight here and say, instead of asking y minus y squared to be small, let's add something to it and ask this bigger thing to be small. That's going to shift the lines this direction. Okay, so we could do this to the other cells. And what we're going to try to do is let's assign a weight wi to every one of these Dirac points. Okay, and different weights are going to cause these lines to shift by different amounts and give us different diagrams with different total mass in each of these cells. Okay, so this object is known as a power diagram or a Laguerre diagram. It's like these reweighted Voronoi diagrams. So let's say we're given a set P. The P is going to be the set of my yi's, y1, y2, up to yn. This is a set of n discrete points that live in Rn. P is going to be consist of all these yi's. Okay, and for the Voronoi diagrams, we were just given this set of points. Now for these Laguerre diagrams, we need also a set of weights. So we're also given this set of weights. Okay, so this is going to be real valued weights. Okay, now we can define this power diagram with respect to the particular weights. Okay, so power diagram, Laguerre diagram. Okay, we're going to say of P with respect to W is, okay, this is where I'm going to start calling them L like I did over here. So again, there are a bunch of cells with respect to these weights, and they're going to consist of all points y in Rn, right, such that, now we almost write down the definition of the Voronoi diagram, but we adjust by these weights. So y minus yi squared minus wi is less than or equal to y minus yj squared minus wj for all j's. Right, so if I just do a 3-mass picture, if I were to give everything equal weight, let's see what would happen. I might get something like this. So this is W equals 1, W equals 1, W equals 1. Okay, but if I take the same masses and now decide to take some weight away from one of them, so maybe these are still equal, this is W equals a half. That means we're trying to take area away from this, so these lines are going to shift this direction. Right, so we're going to get something more like this. That's kind of asymmetric. Right, and still get something like that. Okay, these diagrams let us define a map, right? And they define a map, exactly like this. Is to say, each point defines a region, and we ask that region to map to the point. Okay, so we get a map. Okay, it's defined almost everywhere, and you can decide what you want to do exactly on these boundaries, but those boundaries don't contain mass, right? Boundaries are a set of measures 0. So we get a map almost everywhere. I'm going to call it TW. That maps Rn onto my set of points. Okay, and we're going to define this by TW of a point x is equal to yi if x is in the ith cell. Is that clear? Okay, so if we can we can build these cells. If we're given a set of weights, we can build these cells. Given a set of weights, we have effectively a map. Okay, and I'm going to also define this weight function. It's just going to I'd be for a little bit of convenience later on. So we can think of a weight vector or the weight function. Okay, so W is going to take, I guess, P to R, so the set of points to R. And it's going to just be defined by W of yi is my ith weight. So we can think of this as a vector or a function, kind of whatever's convenient. You look like you want to say something.
Do we have a constraint on the weight functions? It seems that at some point we have to have the balance, because if we move something this way.
Yeah, so what are the constraints on the weight function? So right now we don't have constraints on the weight functions. Indeed, at the end of the day, when we're solving optimal transport, it's not necessarily that this point has to live in this region, right? We could have a set of points that don't overlap at all with the region that we care about. So, of course, it's, for Voronoi diagrams, the point lives inside the region. For these power diagrams, they may not. So we may have weights that let this all shift off to somewhere else. So that can certainly be the case. It's also true that if I take my weight vector and I add a constant to everything, right, I'm going to get the same power diagram, right, because the same constant is going to come off on both sides of this inequality. So these things, in some sense, are only going to be defined up to constant shift, and it doesn't matter what the constant is. But certainly, most of these weights are not going to be useful to us in our optimal transport problem. The goal is, can we find the right weights that do what we want? So yes, what does this have to do with optimal transport? So I said, look, we can kind of break space up into these nice polyhedral regions. That's great. Is that actually what we want? We know that the semi-discrete optimal transport comes down to decomposing our domain into n sets. Now, a priori, it's maybe not obvious why these sets would have to be polygons, for example, right? So we need to show that this is actually a useful formulation. So this is my claim. These types of maps like this are optimal. And what are they optimal for? They're optimal maps between some source measure and whatever its push forward is under this map, right? So once I've given you a set of weights, you've got a map, and the map will take your source onto something, whatever it is. So my claim is going to be that for that particular something, which was, was defined by the W, this is the optimal way of mapping to it. There's not a better way of decomposing space. But that's not you giving me the data, the target measure. That's you giving me the weights and saying, from that, I define a target measure, and now I can tell you what's the optimal map onto that. So there's a couple phases that we have to get through here. I don't know. Most of the time, we've done feasibility first and then optimality. But I guess today we're doing optimality first, and then we'll try to sort out feasibility. No, we don't want overlapping regions, absolutely. I mean, except for on a set of measure 0. Right? These boundaries, it kind of doesn't matter. Because when you ask for mu on the interior of this or ask for mu over the closure of this, it's going to give you the same result. Okay, so this is my claim. Okay, given a source measure mu, some absolutely continuous measure mu, okay, and a set of weights, okay, so we've got our weights, W, and our set of points. All right, given all that, we can define this map. So given this map, we can also define the target measure. So we can define the target measure, nu, to be equal to push forward of mu. So if I'm going to, I'm starting with my map. I'm starting with this. If I'm going to talk about optimal transport, I need a target density that's feasible. So at this stage of the game, I don't have any freedom there. I'm just stuck with whatever the push forward is. Okay. Given this, though, this gives a map. It gives a target density. It doesn't tell us that this is an optimal way of mapping onto this target density. It gives us a way of decomposing space, but it might not be the optimal way for this particular measure. But in fact, I claim that it is. Okay? I'm going to claim that then TW is optimal. Right, so what is this doing? We're given a source measure mu, and we're given some points, but we're not given the lambdas. We're not told how much weight is assigned to each of these. But we're giving a set of weights W, so the weights W lets us come up with some kind of diagram. Okay, and now we can go in here and say, well, how much mass is in each of these? So our diagram, if I bring my diagram out here, the diagram is really going to live in my source. And then I say, well, how much mass is in here? Well, however much mass is in here, so mu of L1 is how I'm going to define my lambda 1. So then I go back to here and I say, I assign you the weight lambda 1. Right, and that's coming up in my and similarly here, I add up the weight in here. However much weight happens to be in here, however much mass happens to be in here, that's what gets assigned to lambda 2. Okay, now I say, okay, great. This gives me a map between this particular measure and this particular measure. But there's lots of ways of mapping between these things that would conserve mass, and there may be a better way of decomposing this. But my claim is, no, actually, this is the best way of doing this. Sure, thanks. Is that better? Not better? Let's see. You want lower, higher? A little bit lower. Yes? Okay, thanks. Okay, so let's try to prove this. Let's try to prove that this is really the best way to partition space. If there's a way to do this using a Laguerre diagram, it's the best way to do it. Do we need to say something about the existence of TW? So I don't think we need to say much about the existence of TW, right? So given weights, we can always define these cells, right? Given these cells, I have an explicit definition for TW. Right? Take any point X, decide which cell it lives in. If that cell was related to a particular Dirac, that's where it maps to. So it's defined almost everywhere uniquely, right? Again, if I happen to pick something on the boundary here, I just pick a cell, and it doesn't really matter. Okay, so T is feasible. By design right now, T is feasible. I'm not saying we can do this for every problem that we encounter, but we've constructed it to be feasible. So what do I need to do? I need to, this is what we always do when we're showing optimality. Here's a map I would like to show as optimal. Let me pick up any other feasible object and try to show that this other feasible object is always going to give me a higher cost than T does. Right? So let's consider any other. Map. So it maps where I need it to do, and its push forward is correct. So S push forward of mu is equal to nu. Okay, so now I need to think about optimality. I'm obviously want to bring in conditions that look like this somewhere. So let's start by saying let's choose any point x in Rn or x in our domain. And what are we going to look at? I'm going to look at objects that seem like this. So what are yi? Yi are the points that the map is allowed to go to, right? The map is only allowed to go to either y1, y2, y3, and so on. So these I could may be useful to replace with the idea of S of x. Let's consider the distance from x now to S of x. Okay, and then wi. W is the weight at yi, or in what we're looking at now, w is the weight at the point S of x, right? So that's why I define this weight function here, needing it to go back and forth between the function and the vector. So I'm going to look at this object, because this is really the object that comes up in the definition of these regions, in the definition of this map right here. Okay, and we know that for some value of j, S is equal to yj. It gets mapped to one of the points. Okay, for some j. And we can do the same thing for the map T, the guy that we're interested in. All right, for some value I, this is going to map to yi. All right, so how is this value that I get with t related to this value that I got from s? Something cyclical monotonicity. I have the definition here, right? So t was chosen to minimize this distance, right? T said, let me look through all the, T said, I know I have to map to one of the y's, y1, y2, yn. Let me cycle through them and pick the one that minimizes this distance, right? Pick the I such that y minus t of y squared minus w of t of I is less than this for all other values of j. That's how we define this map T, by these power diagrams. What's that? It's like a shifted quadratic, yeah. Right now it looks like a shifted quadratic cost. No, we're actually trying to do quadratic cost, so I need to do something about the shift. But of course, I know that I want to do something with the quadratic, but what I've got here is this. So I start with what I got and then see where we could go from there. Okay, so we know TW was, I should have a W. TW was defined as the minimizer of this object. Okay, so we can relate these things. We know that x minus tw squared minus w tw has got to be less than or equal to whatever we get with any other. All right, so this is the case. And now I've got to, this is what I know, I've got to take this and work with what I'm trying to get to. And I know that what I'm trying to get to is something like a quadratic optimal transport cost, which means I'm interested in taking this term and integrating it against mu, right? And what I'd like to say is that this is the map that minimizes that object. So let's start with what we want. What I want is this. Okay, and I'd like to show this is less than or equal to the same thing with S. So right now I can put, I'm moving my weight function to the side. I've got all that extra junk. So what am I going to have? X minus S of X squared. Let me break it up like this. And then I'll put my weight functions together. W of TW minus W of S d mu. I'm running out of space. Okay, this term is the term I definitely want on the right-hand side. This is extra junk that I don't really want on the right-hand side, but what can I do with that? Mass preservation, exactly. So we know that TW pushes forward mu into nu, and we know that S pushes forward mu into nu. All right, so I could rewrite this. On the one hand, I could try a change of variables, let y equal TW, and then I'd be integrating against mu. So I could do, say y against nu. But here I could let y equal S, again, because the push forward is the same, still going to have me integrating against nu. And this is exactly what we wanted to show. Okay, so given any feasible mapping, the feasible mapping will always have higher than or equal to optimal transport cost compared to this TW mapping. We can certainly say TW is optimal. So that's optimality. Are there any questions on the optimality part of this? The quadratic cost doesn't care about a shift in the constant in the weights, you mean? That's right. The quadratic cost doesn't care if we shift the weights by a constant, and that is, it's good to actually think about those things. Is that reasonable for our problem? It is reasonable probably for this setup because also the Laguerre cells, or in other words, the map that we get doesn't care about a constant shift in the weights, right? So a constant shift in the weights, in this, looking at it here, we say that's not going to change the map. And looking at it over here says, well, good, that's not going to change the cost at all. So we have optimality, but for a rather contrived target measure. And now we don't want to work with a contrived target measure, optimal transport problem. You give me the measures, you give me both the measures, and then I have to come up with the mapping, right? Which is not what we did here. We took a strange route through here. Effectively, you gave me one of the measures and you gave me the map, and then I just said, let's just computer push forward. Okay, so that was for a contrived nu. Now, what if we are given nu? Okay, so again, it was going to be of this form. And this time, we don't get to pick the lambdas. They're just given to us. So we're given mu, some nice absolutely continuous measure mu. We're given nu, which is this weighted sum of drafts, and we don't have any control over the weights. We want to construct a map. what do we have freedom to choose or to change to try to get both a feasible and an optimal map?
A partition of the original.
Yeah, we're trying to come up with this partition of the original. We suggested that these power diagrams may be useful. So what do I have freedom with in building these power diagrams?
The weights.
The weights. I have freedom to choose the weights, exactly. So this is what the problem is going to come down to. All right, before, you gave me the weights, and then I used them to construct nu, but that's backwards. What we really want is you give me nu, and now I somehow come up with the correct weights. So we need to find an unknown weight vector such that what? Such that we end up with a feasible map. So you give me any set of weights W, I can define a map. Once I have the map, I can look at the push forward of mu. We need to find the right weights such that we end up with a feasible map. And we know, we just showed, once we have a feasible map that has this form that comes from these power diagrams, it's automatically optimal. Right? So this comes down to a problem of feasibility. Okay, so once we have a feasible map of this form, it's automatically optimal. Okay, so we wrote down earlier what this condition was that we wanted, right? The condition was that we had to look at the push forward measure and make sure it agreed with mu. In other words, we looked at mu of T inverse at yi and said however much mass is in there should agree with lambda I. This is what we're trying to accomplish. So we need to find W that makes this true. So this is a set, right? Oops, whatever the inverse map is of yi. What is the shape of this set?
Polygon.
It's some kind of polygon, and it's a Laguerre cell, right? So this was nothing but the ith Laguerre cell with respect to the weights W. So this is our real goal. Let's find the weights W such that mu of Li of W is equal to lambda I. Okay, if we can do that, then we're done. We have our optimal map. Okay, so we're actually going to do this constructively and see if we can come up with an algorithm for building these weights. And if the algorithm converges to the right thing, then we've not only have we computed these weights, but we've sort of constructively showed that actually they exist. This form of map actually does exist for us. So this is more or less going to be the method of Oehlers and Pressner from, I think, 88, which is basically the first numerical method out there for solving the Mosier-Ampere equation. It was this setting and effectively trying to build up these weight vector. I think the notation is a little bit different, but the idea was exactly this. So this is going to be the idea of the algorithm. We're going to pick a reference point, y1, and we're going to assign most of the weight to that point and hardly any weight everywhere else. And then we're going to slowly, gradually transfer weight to the other points until we manage to hit this condition. Okay, so let's pick a reference point, doesn't matter which one. okay, and give it most of the weight. Right, then what do? We gradually add weights to the other points. Okay, and recompute these Laguerre cells. Okay, so let's say I have 3 points. The picture would be this, that I'd have 2 really tiny regions, and then L1 would be everything else. Then in my next iteration, I'd look at this and say, these guys don't contain enough mass. We need to give them more mass. We need to up the weights here. So we try to up the weights, and those cells get a little bit bigger. And we look at everything again, and we say, well, they still don't really have enough mass. So we shift them again, and it will come down to just taking these lines and trying to shift them out to enlarge the cell. You can almost write down the algorithm by a picture more easily, I think, than you can sort of abstractly and rigorously. Okay, as in many of our algorithms, we're not going to try to do this exactly. There's going to be some tolerance, some epsilon, some relaxation, and we're going to try to get close. So let's pick a tolerance epsilon. Now, our algorithm is we're going to have a sort of feasibility condition for our algorithm that has to respect. It has to keep these cells small, right? We'd like equality here, but we're always going to try to come at the equality from below here, okay? So these are always going to be a little bit too small, or at least not exceeding it by too much. So this is going to be what we require. At each step, we're going to require L2 through Ln. Right. L1 gets treated differently. He's big. These guys are small. Okay, to be small in the sense that the mass in each of these is going to be less than or equal to the required mass plus epsilon. Right? So L1 is allowed to wildly overestimate his mass here, and obviously we hope that by the time the method converges, it's not wildly overestimating anymore. But these aren't. They're allowed to get bigger. They might get a little bigger than lambda, but never by more than epsilon. So this should be true for I from 2 to n. Okay, and our goal is going to be to keep shifting weight around. Let's keep shifting weight around until we get within our tolerance. Let's keep shifting weight until this happens. That not only does it not overestimate it by more than epsilon, but it doesn't underestimate by more than epsilon. So in other words, mu of LIW minus lambda I. Okay, we may not hit 0, but we get this within epsilon. And this is going to, again, be true for I equals 2 through n. Okay, so for these cells, most of these cells, we come within epsilon of our mass balance constraint. We should check what happens with this guy too. How far off is he? So we know this. We know that if we add up the mass in here plus the mass in here plus the mass in here, it's equal to 1, right? We've got probability measures. So that means that if I look at L1, the mass in here is going to be 1 minus the sum of the other regions. So if this is our termination condition, when this happens we stop, then let's see what that says about L1. How good is it? Okay, that means that if we hit the termination condition, then we're also, so most of these guys are accurate to within epsilon. We want to know, well, what about L1? Okay, so we have an expression for mu of L1. Let's see. I'm going to write 1 in a different way. I'm going to write 1 like this. Right, the sum of the lambdas is equal to 1. We're going to subtract off the mass of the other cells, and we're going to take off this lambda 1. Right, so that's an expression for how accurate the mass of this cell is going to be at the end of the day. Okay, this I can put together under one sum. What do I have? I have sum of Li minus mu okay, I have bounds on every term in the sum, right? They're in magnitude always less than epsilon. There's n minus 1 of them. So this is bounded by n minus 1 times epsilon. Okay, so if I can do this, if I can come up with an algorithm that achieves this as my termination condition, then we're in good shape. The mass of all the cells can be made, the mass of the error of the mass in all the cells can be made arbitrarily small depending on the tolerance that we pick. This is okay? Okay, so let's try to come up with an algorithm. Okay, we need to initialize. Okay, so I'm going to fix the weight at this point, the weight W1, and I'm never going to change it. So remember, the weights are defined up to a constant shift, right? So I can do this. I'm going to say W1 is equal to 0, and that's fine. All the rest of the weights will have to shift relative to that. But there certainly is a solution that has W1 equal to 0. So we're looking for that solution. I could have picked something else than 0. It doesn't matter. So we're going to fix W1 equal to 0, and we never ever touch this again. What we are going to touch, we're going to start with these weights probably being very negative, for example, and then we're going to keep bringing them up, bringing them up, bringing them up until they get where we need them to get. Okay, so how are we going to initialize these cells? We want to do it in a quick, easy way. It's usually not preferable for all your computational power to be going into your initial guess, or sometimes the initial guess can be a hard problem in and of itself. So let's consider this set. I'm going to decide how much weight to, for each yi, I have to decide how to initialize its weight in a way that's guaranteed to satisfy this condition. And I don't want to have to look at the whole diagram to assign all of these weights. I don't want to have to look at L2, but also compare it to L1 and L3 and L4 and so on in order to decide on its weight, because that's too much work for an initial guess. So let's simplify things down a little bit. Let's consider this sort of reduced power diagram where I'm only comparing the ith point, the point where I'm trying to initialize its weight, to the first point, this sort of fixed reference point. Okay, so I'm going to call this L tilde W. So this is going to be the set of y, such that y minus yi squared minus wi. Now, instead of comparing it to all the j's, I only compare it to the first guy, to my reference point. Okay, and W1 we decided to make 0, so that's not even there. Okay, so if this is yi and this is y1, these guys are easy to construct, right? Just depending on what W is, we drop a hyperplane between them and move it left to right, up, down, whatever direction we're in, depending on W. So these cells are easy to compute. Now, what do I want to do? I want to shift this over here, because I want most of the weight to be assigned to this guy, and I don't want very much over here. So we're going to try to move him that direction. Okay, and let's choose Wi such that the mass over here satisfies this condition. Okay, so such that mu of this set, the measure of this set, which is very, very easy to compute, okay, is less than or equal to, this is a tilde, lambda I plus epsilon. Right, so that means I take each point in its turn, I ignore all the rest, drop a hyperplane between these, and slide it over till I've got almost no mass left in here. And in practice, I've probably got a bounded domain. Right, so I'm going to slide this hyperplane over till it's just hitting a corner of the domain. And there's hardly any mass left in here, and y1 is taking over all of the weight. This step doesn't have to be particularly precise. We just need to make this happen. Okay, so I do this for all of my i's. For I equals 2 through n, I give them all some ridiculously small weight. Now these are artificial cells, right? The real cell, we need to work with the real cells, and we need to show that the real cells satisfy this condition. Of course, they are going to satisfy this condition, right? Because adding in more constraints is going to say, well, if we have to look at W, if it also has to be smaller than when we have Y2, that can only add another line here that chops more out. I can write that down precisely. Okay, so does this satisfy the sort of full feasibility condition for our algorithm? Well, let's take a point that lives in this cell that we actually care about, the full Laguerre cell. And we're going to show that it's constrained also to live in this simplified cell, which means the mass of that is going to be less than the mass of this because the cell is contained within here. So let's choose any y belonging to LIW. That means, by definition, that this is the case. Right, and in particular, if this has to hold for all j, it holds for j equals 1. So this means, in particular, this is certainly true if we just compare to y1. So that means this point that lived in our full Laguerre cell also lives in this simplified Laguerre cell. So y certainly lives in this simple cell that we used to initialize. Okay, in other words, the real cell we care about is a subset of our dummy cell that we used to initialize. And that means that if I look at the mass of this, it's going to be bounded by the mass in my dummy cell, which was chosen to be sufficiently small. Okay, this is true for all I between 2 and n. So what does that mean? Our initial guess follows the rules. Right? We want an algorithm that always preserves this property, while hopefully getting closer and closer to this. But if it always preserves this property, we better have it to start with. And we do. So we have an initial guess that is perfectly allowed. Okay, now how do we update? Okay, so this was our goal, remember? We want to find weights so that mu minus lambda is bounded by epsilon. I'll write it like this. It's not that terribly critical, whether it's strict or non-strict inequalities. One direction we always have. We're going to require our algorithm to always preserve this one direction, and we're going to hope that we end up with this direction. So here is our update rule. So our update rule is we're currently holding a set of weights that came from somewhere. Maybe it's from our initial guess. Maybe it's from the last step that we just did. We use them to update our power diagram. You need to know how much mass is actually in all of these cells. Again, this is sort of maybe a convenient point. The cells are actually polyhedral, so that means that if we're integrating over them or need their volume or something, that's actually relatively straightforward to do. Okay, so we have a power diagram sitting in front of us. I'm going to just draw a dummy one with 3 points over here. Because again, the picture is actually the easiest way to write down the algorithm. So I have my 3 points, say, and I have a current division of them. Now, all right, this is satisfied for all of them. I'm going to pick any point where this fails. It doesn't matter which one. You don't have to go through an order, whatever you want to do. So let's choose any value of I such that, okay, not quite any value of I. We're not messing around with I equals 1. okay, such that mu of LIW is violating this condition. So in other words, it's less than or equal to Li minus epsilon. Right? We want it to be bigger than or equal to Li minus to epsilon. This difference to be bigger than or equal to minus epsilon, but right now we're missing the mark there. So we know that we need to play with this weight at this point. So let's say this is the point I picked. Looked at this. I said mass is too little here. So what am I going to do? I'm going to take these lines and I'm going to start sliding them. Right? And I'm going to keep sliding them until the mass gets big enough. So I slide them out, I slide them out. So I'm effectively updating my Laguerre diagram, which is not a global beast here. I'll say two things. There's packages out there, geometric packages that do these things for you efficiently. You know, that compute Voronoi cells or weighted Voronoi cells or things like this. But in a case like this, we're kind of updating things locally. So I'm just shifting the lines near yi, which in principle it could consist of n of them, but in practice it's typically going to consist of a small number of them. There could be some little topology changes that you have to deal with, where you lose an edge or something. But we're really just shifting things locally. And we'll keep doing it until we're happy that we have enough mass. So let's keep increasing Wi until the value of the mass in here hits an acceptable level. In particular, we're going to bring it up above lambda, but not too far above because we're never allowed to go too far above. Okay, so what have we done? We've gotten this guy to have an acceptable level of mass. Of course, we've messed with some of these guys, right? We may have brought down the mass of some of these guys. Now, fortunately, we haven't brought up the mass of any of the other cells, right? If the other cells started out obeying this condition, now we've shrunk them, so they're still going to obey this condition. But in any case, we've increased one of the weights. Okay? And then we keep going. So now this side has an acceptable level of mass, but some other ones may not. So we go through and we just find one that doesn't have an acceptable level of mass. We increase its weight until we get it up to an acceptable level. And we keep going through, bouncing through our diagram and saying, you're too small, I lift your weight. You're too small, I lift your weight. The weights are always, always increasing. Okay, and we repeat until we hopefully achieve our termination condition. So that's the algorithm. Are there any questions on the basic algorithm?
How do you prevent when you already increase one of them and then try to increase the other? Will it mess up with whatever you did before?
So when I do this, will I mess up with whatever I did before? So that's not obvious at initially looking at this, right? So I'm looking at this picture, and maybe there's so little mass in here that I zoomed this out until I obliterated some of these other cells, right? That's not obvious from the picture that can't happen. All that's obvious is that certainly I haven't broken this condition anywhere else, but I may wildly made this condition worse. So yeah, we have to do analysis to decide, is this actually going to work? You know, I'm increasing the W's, but are they converging to anything, or are they just bouncing around forever and not getting anywhere? So this step is very, very suspect right now. We certainly, I didn't write it, but I said it, until hopefully we achieve termination. Any other questions about the basic algorithm? You know, this isn't pseudocode, right? within this, you're going to have to either write your own methods or probably use packages that are out there for constructing these power diagrams and things like this. If we're doing, quadrature or something to compute these measures. But yeah.
Do you run through the n multiple times?
Do you run through 2 to n multiple times? Yeah, you might. It all is, I mean, right now we don't even know if the algorithm terminates, so it might just keep cycling through all of them forever. We don't know that yet.
It's not like when you hit the target mass for one, you can't just discard it out of your algorithm.
Right, so the problem is once I hit the target mass for this one, now in my next step, I might come over here and say, this guy has not enough mass. So actually I'm going to take this line and move it back, and I'm going to take this line and move it back, and now I've shrunk his mass up, right? So that could happen, right? They get bigger, but then the next step makes it smaller again. So we certainly have to do analysis, and we certainly will do analysis to decide if this works, because I wouldn't. The picture makes it obvious what the algorithm is. It doesn't make it obvious that this algorithm actually converges to what you want it to.
You can just wiggle one line until you might hit something you want. You gotta shift it back and forth.
Can we wiggle one line? That is very mathematically precise language that I appreciate. So I would say, once we start doing the analysis, it will end up being fairly easy to analyze this and show that actually, even with this jumping back and forth in this precise way, that the reason we're moving all these lines out and not just wiggling one or the other is because we're trying to end up with a Laguerre diagram, right? So what we have freedom to choose, we don't have freedom to just wiggle the lines wherever we want. We have freedom to change the weights, right? Changing the weights is going to cause all of these lines to move. Yeah, so when I change the weights for the other one, it will change the conditions for every other one of them, potentially. So I'll say this. You guys are worried about convergence. I'm really glad that you're worried about convergence. That makes me feel like you've been trained pretty well here. If you were just blindly nodding your head and saying this is good, then I would be concerned. So what we're going to do, but not today, is check two things. Two things over probably more than two steps, but two big things is our feasibility condition preserved? Okay, I think from the picture it's obvious that it probably is, but we should actually check it, because obvious from the picture is not a mathematically precise way of doing things. Although I like the picture proof. So we'll check that that's preserved. That's not hard to check. And then the big question is, does this happen? Do we actually terminate, or do we just wiggle these things around forever? Does the algorithm actually terminate? Right? And what makes it terminate? It terminates if it can't find anything more to update. Right? So this feasibility preserved means this is always true. We terminate when this condition is true, when all of the masses are sufficiently big. This minus what we want it to be is bigger than minus epsilon. So that's our termination condition. So if the algorithm, if these two things are true, if we preserve feasibility, if we terminate, then at the end of the day, all our masses are going to be in the region that we want them to be. And then we're going to say, okay, to within this tolerance, we've computed an optimal transport solution. We have like 3 minutes of class time left, and I cannot prove these things in 3 minutes. But I promise I'm planning to prove them for you. And hopefully this doesn't haunt your nightmares too much over the next 2 days waiting for it. So we'll finish up analyzing this next class, and then we're going to talk about how to take this basic framework of this Laguerre cell approach to semi-discrete optimal transport and speed it up, because this may not be fast.